So, we will see how this expression rho b v dot n dA integrated over the control surface, how does it automatically take care of inflow and outflow. We had two different terms for inflow and outflow, now we have only one term, but that automatically takes care of outflow and inflow. Okay. As earlier we will start with outflow, which is easier to explain first. This is the control volume and this is the outside, and there is outflow through this control surface, okay, and that is why we have drawn an outward normal here. So, inside of control volume and outward normal for this control surface. Now, what I have shown here are few typical velocity vectors. Because it is a outflow surface, velocity fluid can flow along this direction, can flow along this direction, along this direction, along this direction. And what is shown is also the angle theta between the normal vector and the velocity vector. Now, based on this configuration, you can easily conclude that angle theta is going to be less than 90 degrees for this configuration, and which means for the outflow control surface, and that is what is also shown here in another way from this book. This is the outward normal to the outflow control surface, this is the direction of outflow vectors, and this angle is less than 90 degrees, which means that v dot n is going to be positive. So, this expression, integral expression, is positive for outflow, positive for outflow. Let us see what happens at the inflow surface. This is the control volume, and so this is the inside and this is the outside, and remember we always draw outward normal. So, this normal points away from the control volume, and this surface represents the inflow control surface. Now, here again I have shown different possibilities of direction of inflow velocity vectors, and to represent the angle, to find out the angle, I have extended them here. The velocity vectors have been extended in this direction, and the angle between the normal and these extended velocity vectors is shown. Now, what is the value theta can take? Based on this configuration, you can easily conclude that theta will be always be greater than 90 degrees, which means that v dot n will be negative. So, this expression will be negative for the inflow surface. So, v dot n automatically takes care of inflow and then outflow boundary based on the angle, and another representation of inflow boundary is shown here, and once again the angle between the normal vector and the velocity vector will be more than 90 degrees, resulting in v dot n less than 0. So, this expression for the inflow boundary is negative, and this expression for the outflow boundary is positive. Let us see what happens at the walls, and that is what is shown here. At the walls, we have said the fluid clings to the surface of the wall, which means that the velocity is 0 at the surface of the wall, which means that there will not be any contribution from this term. If the fluid flows or slides along the surface of the wall, then the angle between the normal vector and the velocity vector is 90 degrees. Once again v dot n is 0. So, whenever you have a wall, either it clings to the surface of the wall or it slides along the surface of the wall, in both the cases this term will not contribute, and that is why we represented in the previous case summed up just control surface out plus control surface in as control surface, because you do not have contribution from the walls where there is no either inflow or outflow. Now, because this expression is positive for outflow and negative for inflow, this integral represents net rate at which property leaves the control volume through the control surface. That word leaves is important, because if this is positive, which means there is outflow through the control surface. If it is negative, which means there is inflow. So, there could be some surfaces where there is inflow, some surfaces where there is outflow, and for all the inflow this will be negative, for outflow this will be positive, and if this turns out to be net value after taking care of all the outflows and inflows, If it is going to be positive, which means that there is a net outflow of the property from the control volume through the entire control surface. No longer we say in or out. So, net rate at which the property leaves the control volume through the control surface. We do not say inflow or outflow, it includes the entire control surface. Okay. So, having discussed in detail I would say the new term, other terms are known to us. Let us look at the physical significance. We have discussed that a few times. Just to summarize here. So, this is the general form of the Reynolds transport theorem. General form, I mean, is applicable for a general control volume, means that now we are allowed for any part of the surface to be inflow, any part of the outflow, which means any number of inlets and outlets. We are allowed for variation of properties across inlet surface, outlet surface. We also allowed for any angle between velocity vector and the normal to the face. So, whatever assumptions we had, we have all taken care of that now. Now, the left hand side represents the rate of change of the extensive property of the system. Okay. I specifically added the word time, because the moment you say rate of change, usually it means with respect to time. To be more explicit, included the word time rate of change of extensive property of system, okay, d by dt. Okay. And how do you quickly interpret? You are taking a small volume dV, multiplying by density, you get a mass of the small volume, multiply by the property per unit mass, you will get the property for the small volume, integrate over the entire volume, you get the property for the system, and take d by dt, then that gives you time rate of change of extensive property for the system. Why extensive property? This represents extensive property, this is intensive property. Analogously, that is for the system, rate of change of extensive property of system. Now, similarly, take a small volume in the control volume, multiply by density, multiply by B, that gives the amount of property in the control volume, a small volume. When you integrate, gives the amount of property in the entire control volume. Take time derivative, gives you rate of change, more specifically time rate of change of amount of property in control volume. Some time back discussed, we usually say extensive property of system, we do not say property of control volume, not so very correct. We say property in control volume or property of contents of control volume. Yeah, and we have discussed in detail the significance of this term rho b v dot n dA, which represents, as I told you, the net rate at which the property is leaving the surface of control volume. We have seen why is it leaving, because its v dot n is positive for outflow and v dot n is negative for inflow, that is why it is leaving. Why is it net rate? Because part of the surface that can be outflow, part of the surface that can be inflow, and of course, that is why it is net rate at which the property is leaving the surface of control volume. How do we interpret this? We take a small area, okay, and then let us say velocity, taking into account the projection of velocity along the direction of area. So, this gives the volumetric flow rate. You have area multiplied by velocity. When I say velocity, along the normal direction to the area. So, this gives you a volumetric flow rate. You multiply by density, you get the mass flow rate, and then when you multiply by B, which is property per unit mass, you get the rate at which the property leaves, enters, etc. And when you integrate the entire surface, you get the net rate at which property is leaving. So, that is why to distinguish this rate and this rate, specifically I have used time rate here and time rate here. These two represents rate of change with respect to time, because of with respect to time there is variation in the property of system and property in control volume. This rate is because of fluid flow. So, this rate is because we have a fluid flow, a flowing fluid has with it associated mass, momentum, energy, and then species mass. So, whatever carried by the fluid flow is represented by this integral. These two represents whatever change with respect to time, one for system, one for control volume. Okay. Well, let us look at two special cases of the Reynolds transport theorem. So, let us write down the Reynolds transport theorem first. Rate of change of property for the system is equal to rate of change of property for the control volume plus net rate at which the property leaves the control volume through the control surface. Okay. What is the first special case? Suppose let us say we are going to apply this Reynolds transport theorem for a tank, and let us say the tank is operating under steady state condition, and since the tank is operating under steady state condition, when I say tank, it is a control volume, this term is 0, and so we are left out with the left hand side rate of change of property for the system, and right hand side we have only the term corresponding to the net rate at which the property leaves the control surface. Okay. Now, these two now become equal. So, under steady state condition, rate of change of property for the system and net rate at which the property leaves the control surface both are equal. Now, depending on the property, the left hand side may be 0 or may not be 0. Suppose we are applying for mass conservation, then we know that rate of change of mass for a system is 0. So, this left hand side will be 0. So, net rate at which mass leaves the control surface is 0. But suppose we are applying this for a momentum balance, then the left hand side we have seen from the law of physics that the rate of change of property, in this case momentum, is equal to sum of forces, which means it is non-zero. So, in that case the net rate at which momentum leaves the control surface will be equal to the sum of forces. So, this net rate at which property leaves may be 0 or may not be 0 under steady state condition. Now, let us look at the second special case, a batch condition. What does it mean? We have a tank, there is no inflow and outflow, that is what we mean by batch condition, which means that this term is 0, there is no inflow, there is no outflow. So, this term which represents the net rate at which property leaves the control surface, that term is 0. So, now what are we left with? The left hand side we have rate of change of property for the system, and right hand side we have rate of change of property for the control volume, and both of them are equal under batch condition. There can be another situation where both of them are equal, where there is inflow and outflow, but it so happens that the net rate of flow is 0. Once again, under that condition, the rate of change of property for the system and the rate of change of property for the control volume both are equal. Okay. Now, if you look at the Reynolds transport theorem, the rate of change of property for the system and control volume are same, but for this term which represents net rate at which property leaves the control surface. Okay. Otherwise, both of them are same. So, this term is what makes a difference between the two time derivatives. So, since in this condition, batch condition, or where the net rate term is 0, then the rate of change of property for the system and control volume both become equal. Now, once again, whether the left hand side is 0 or not depends on the property for which we are applying. If we are applying for mass balance, the left hand side is 0, the rate of change of property for the system is 0, and so rate of change of property, in this case mass, rate of change of mass for the system is 0. So, the rate of change of property, in this case mass, that is rate of change of mass for the control volume is also 0. Suppose we are applying for energy balance, okay. What will happen? The left hand side is rate of change of energy for the system, which is non-zero, because that is equal to the net rate at which heat transfer takes place, work transfer takes place. So, which is non-zero. So, in that case the rate of change of energy for the control volume will be equal to net rate of heat transfer and work transfer. So, the left hand side could be 0 or non-zero depending on the property or the balance for which we are going to apply this equation. Now, what we are going to discuss here is the relationship between the substantial derivative and Reynolds transport theorem. We have discussed the substantial derivative few classes earlier, and just now we have discussed the Reynolds transport theorem. There is a relationship between these two, and that is what we are going to discuss now. So, let us write down the substantial derivative for a property B. The substantial derivative is given by capital dB by dt, and if you expand that, the right hand side we have dou B by dou t, and then we have Vx dou B by dou x, Vy dou B by dou y, and Vz dou B by dou z. Now, let us write down the Reynolds transport theorem also, and then let us discuss the relationship. Rate of change of property for the system on the left hand side, rate of change of property for the control volume, and net rate at which property leaves the control surface. Now, what is the significance for the substantial derivative? dB by dt on the left hand side represents rate at which property changes as you follow a fluid particle. Okay. The fluid particle is important terminology here. So, we applied the substantial derivative, or we derived it for expressing the rate of change of property as we follow a fluid particle. So, the left hand side is a Lagrangian representation, tells about how property changes as you follow a fluid particle. Right hand side we said it has two components, two contributions. The first term represents the local contribution, that is because of the unsteadiness of the field. When I say field, it could be temperature field, velocity field, whatever field we are applying for. And the next set of three terms is because of convection, because of fluid flow. Okay. So, first component is because of the unsteadiness, which is local component. The second contribution is from the convective component, and the two contributions on the right hand side are the Eulerian representations. So, as we discussed, substantial derivative expresses a Lagrangian derivative in terms of Eulerian representation. Left hand side we have Lagrangian description, right hand side we have Eulerian description, and that is what is shown here. D by dt relates Lagrangian description to Eulerian description. Now, let us look at the significance of the Reynolds transport theorem. The left hand side is rate of change of property for a system, which is once again a Lagrangian description or Lagrangian concept, and right hand side the two terms correspond to the Eulerian description, because they are for a control volume and then corresponding control surface. What is significance of the left hand side? Rate of change of property for the system, and right hand side we have rate of change of property for the control volume, that once again represents the unsteady component, because that component arises because of the transience, okay. And the second component arises because of flow through the control surface or because of convection. So, left hand side is Lagrangian representation, right hand side is Eulerian representation, and we have written the Reynolds transport theorem for a system. Okay, now, let us compare both the, and that is what is shown here. Reynolds transport theorem relates a system analysis to a control volume analysis. Now, let us look at the analogy between the two. The substantial derivative also left hand side was Lagrangian representation. In the Reynolds transport theorem also the left hand side was Lagrangian representation. Coming to the right hand side, in both the substantial derivative and the Reynolds transport theorem, they represent the Eulerian representation. even in terms of contribution, we have two contributions in both the cases. The first contribution is the local contribution or unsteady state contribution. Second contribution is from convection or because of fluid flow, okay, and that is what is shown here. The total rate of change of property following fluid has two contributions, local or unsteady part and then the convective part. So, both in terms of description, that is the left hand side is for Lagrangian and right hand side is for Eulerian in both the cases, substantial derivative and Reynolds transport theorem. Not alone that, in the right hand side even the two contributions are analogous. What are they? The unsteady part, the local part and convective part. Now, what is the difference between these two? Now, if you look at the substantial derivative, as I told you, the key word is fluid particle. The substantial derivative is for a fluid particle. Okay. The Reynolds transport theorem we have written for a finite size system. Fluid particle are infinitesimal. So, more precisely infinitesimal fluid particle. The Reynolds transport theorem is for a finite size system. Now, if you recall back, we said a system can be considered to be consisting of several fluid particles, and that is what is represented is brought out here as well. So, while d by dt is for a infinitesimal fluid particle, the corresponding integral representation is the Reynolds transport theorem for a finite size system. So, d by dt is for infinitesimal fluid particle. To use a formal word, the integral representation, whenever we say integral, it is for a finite size. So, the integral representation of d by dt is the Reynolds transport theorem. Now, looking at the other way, suppose if you take Reynolds transport theorem and make the volume shrink to 0, you will get the substantial derivative. In fact, that can be mathematically proved. So, if you want to go from Reynolds transport theorem to the substantial derivative, you shrink the volume to 0. So, you have finite size system, there are several fluid particles, you make it to 0, which means you will have only one fluid particle, and that is what the substantial derivative represents. Okay. So, in terms of physical significance, they are analogous. In terms of size, they are different. One is for infinitesimal fluid particle, the other one is for finite size system, and that is the relationship between d by dt, the substantial derivative and the Reynolds transport theorem. Okay. And this is what is shown in this figure, a nice representation from this book Sengal and Simbala, Fluid Mechanics Fundamentals and Applications. And that is the reason we discuss, because we have discussed d by dt sometime earlier, now we are discussing Reynolds transport theorem. So, want to emphasize the analogy between these two and what is the what they are different in terms of I would say scale, length scale. Okay. One is that very small infinitesimal particle scale, other is a finite system scale. That is why whenever we represent fluid particle, we represent by a dot, but finite system we will represent by a region. Okay. We have discussed the significance of B. We said capital B is extensive fluid property, which could represent total mass, total momentum, total energy, total species mass. In terms of variables, they are mass multiplied by 1, velocity, the internal kinetic potential energy per unit mass, and then the mass fraction of species. What does B represent? The intensive fluid property, the extensive fluid property per unit mass, and it B, the same equation represents, or we are going to use it for different values of B, namely for mass, total mass it is 1, for momentum it is V vector, and for energy it is sum of all this internal kinetic and potential energy, and for species it is this mass fraction. Of course, both are related by B equal to m into B. This equation the Reynolds transport theorem, this equation which represents the Reynolds transport theorem is a starting equation for the derivation of all conservation equations, which we will see as we go along. Of course, it looks little scary. You have a integral expression, and that integral expression is within a differential expression, and that likewise you have two expressions, one on the left hand side, right hand side, you have another integral expression. So, the look of it looks little scary, but you will see that we will simplify them when you come to applications. We will apply this for deriving the conservation equation for mass, momentum, energy and species mass, and when we apply we will simplify that and becomes very easy for application. Okay. So, that brings us to the close of this part of the fundamentals. We defined and discussed system and control volume, system made of specific fluid particles, control volume, different fluid particles pass through, and we discussed the need for Reynolds transport theorem, laws of physics are formulated for a system, and Reynolds transport theorem relates the laws of physics as applicable to a system to the conservation equations applicable for a control volume. I think now this sentence makes more sense now. The derivative to the left hand side was for system, the right hand side all related to the control volume. How exactly we are going to apply that we will see as we go along. We derived the simplified form of Reynolds transport theorem, making assumptions, and then extended the Reynolds transport theorem for a general control volume. Okay. So, this brings us to the close of the first part of the course on fundamental concepts. Let us quickly summarize them. Start with continuum hypothesis, which ignores molecular structure and assumes matrix continuum. We looked at two approaches for describing fluid flow, namely Lagrangian and Eulerian. Looked at the substantial derivative, which is derivative following the fluid motion. We looked at different ways of visualizing flow patterns, namely streamlines, path lines and streak lines. We distinguished system and control volume, system made of specific fluid particles, different fluid particles pass through a control volume, and finally the Reynolds transport theorem, which links the laws of physics for system to the conservation equations for control volume. I wish to emphasize that almost all the topics which are discussed under fundamental concepts are not restricted to fluid mechanics alone. Usually we discuss all these topics under fluid mechanics, but should be kept in mind that almost all the topics except possibly visualization of flow patterns, all the topics are not restricted to fluid mechanics alone. They are applicable to flow of fluids, flow of energy and flow of species mass as well. For example, when we discussed Lagrangian Eulerian, we took examples of temperature measurement, concentration measurement. Substantial derivative, we discussed about derivative following the motion for the case of temperature, concentration, of course velocity as well. And similarly the concept of system and control volume and Reynolds transport theorem are generic, and in fact the Reynolds transport theorem is going to be applied for the derivation of conservation equations, all the conservation equations for mass, momentum, energy and species mass. So, and that is why all these topics have been put under fundamental concepts, so that these concepts can be applied and for the derivation of conservation equations of total mass, fluid momentum, energy and then species mass.